Assalamualaikum and hi everyone. In this lesson, you will learn numerical solution of ordinary differential equations. Okay, before we go to the numerical solution, let's look at what is ODE, ordinary differential equation. Okay, ODE is a differential equation that contain one or more functions of one independent variable and the derivatives of those functions. So for ODE, we have one independent variable only. Let's look at these examples. For the first example, we have 4d cubed y over dx square, dx cubed plus dx dy dx minus y equal to 0. So you can see here, y, we differentiate y to x. Here, y to x also. So y is the dependent variable, because y depends on x and x is the independent variable. Okay, for ODE, we have only one independent variable, which is x. Okay, for second example, okay, del u over del x equal to a del square u over dt square. So u over x and u over t. So here u is the dependent variable. Okay, u depends on x and also t. X and t is the independent variables. So this example is PDE, partial differential equation. Okay, solution of this ODE is y. Is the dependent variable. Dependent variable, okay, for this example, equal to y. So we want to find value of y. Okay, let's look at the applications of ODE. Okay, you have learned in Math 2. The first one is growth of population. Okay, and look at this equation. This is rate of growth. P is the independent variable. Dependent variable. P differentiate to T. T is the independent variable. We have only one T. So this equation is ODE. To find the solution, look at here. We want to find the solution of ODE. So what is the solution? The solution is the dependent variable. That's why I teach you about dependent and independent variable. Dependent variable is the solution. Okay, for this growth of population, we want to find P. P is the population. For second example, Newton's law of cooling. Okay, second application. This one is also ODE, where we want to find theta. Theta is the solution, which is the temperature. We want to find the temperature. So for this example, for this equation, we want to find y. Okay, in this lesson, you will learn how to solve the initial value problem. Okay, the initial value problem is ODE. ODE plus initial value. Nama dia IVP pula. Initial value problem. ODE together with initial condition. So this is ODE and this is the initial condition. These are examples of IVP, okay, given the ODE and also the initial condition. Okay, there are many methods to solve ODE. Okay, but you will learn Euler's method and also Runge-Kutta method. Okay, the solution is an approximate solution. When you use Euler method and also Runge-Kutta method, okay, the solution is approximate. We just if you use numerical solution, you can get approximate solution, not the exact solution. So basically, today you will learn how to solve this type of equation. Okay, let's look at Euler method. Okay, this is first order numerical method and the most basic. Okay, this is the most basic numerical solution to solve ODE. And Euler method is explicit method. I will explain about this later. Okay, look at the definition. Let H be the step size. The Euler's method for solving IVP in the interval AB can be defined as this one. So you will determine the next y by using this formula. Okay, given x naught, y naught from the initial condition, and then using this one, you will determine what is y1. And then using x1 and also y1, you will determine the next y2 and so on, y3. Okay, so this is y that we want to find, yi plus 1. Yi is the previous solution. And then yi prime is from the IVP. So we have y prime equal to fxy. So you determine yi prime here. Take this value. Okay, you take this term. And then step size. Okay, for Euler method, the step size is important. Okay, if you decrease the step size h, you will improve the accuracy of the method. However, it requires more steps and more time to compute the solution. Okay, later you will see the example. If you use larger step size, it will produce inaccurate solution. Okay, let's look at example 1. Find the approximate solution of this IVP, initial value problem. This is the ODE. And this one is the initial condition. By using Euler's method, it x equal to 1.3. And the step size h is 0.1. So we want to find what is value of y when x equal to 1.3. This is the initial condition. So when x equal to 1, x naught equal to 1, y naught equal to 2. Here is the y prime. Y prime equal to 3x square y. Okay, you can draw a table like this. Okay, put I, xi, yi, and also yi prime. And then first, you must determine value of x here using h. Right, the first x is from the initial value, which is 1. When x1, y equal to 2. So y equal to 2. And then we want x at 1.3. So for the next x, the next value of x is 1 plus 0.1, which is 1.1. After that, 1.2 and 1.3. So we want to find this y. Y here. Okay, this is x naught, 1, 2, 3. So from initial condition, okay, from initial condition, y1 equal to 2. So x naught equal to 1, y naught equal to 2. And then we want to find y naught prime. Okay, because we want to determine y1. For next step, x1 equal to 1.1. So y1 equal to y1. Okay, we determine y1 using the equation. y1 equal to y naught. Remember this y1 is the previous solution. So y naught plus h y naught prime. Okay, that's why you must determine y naught and also y naught prime. Okay, kita dah ada y naught, then you must find y naught prime. Y prime is from the question, this one. Y prime equal to 3x square y. So substitute 3x here is 1. So 1 square y is 2. 2. Can you solve? You will get 6. So y naught prime equal to 6. Put in your table. Okay, next, using y naught and also y naught prime, you can find y1. So y1 equal to y naught is 2 plus h is 0.1. 0.1 multiply with 6 equal to 2.6. And then put in table 2.6. Next, you must find y1 prime using this equation. y1 equal to 3. Here x is 1.1. 1.1 square. Y is 2.6. 2.6. Okay, then you calculate using calculator, you will get 9.438. This is 9.438. x2 equal to 1.2. And then find y2. y2 equal to, remember for y, to calculate y1, y2 and so on, we use this formula.
y1 plus h
y1 plus
plus
h
h y prime y1 prime.
y1 prime. Okay, good. y1 is the previous solution here. 2.6. 2.6 plus 0.1 multiply with y1 prime. y1 prime is 9.438 equal to 3.5438. So y2 is 3.5438. Okay, next, find y2 prime. Okay, using this equation. 3x square. X is 1.2 square multiply with y2. 3.5438 equal to 15.3092. Masuk dalam table 15.3092. Next, x3 equal to 1.3. And then we want to find y3. y3 equal to y2 plus h y2 prime. Equal to y2 is 3.5438 plus h is 0.1, y2 prime is 15. 15.3092. So the answer is 5.0747. This is the answer, 5.0747. Okay, next we go to Runge-Kutta method. Okay, this is one method to solve ODE, numerical solution of ODE. And to determine the next y, we use this formula. Okay, here is the, macam tadi kak, this is the previous solution. And you must calculate K1, K2, K3 and also K4 using this formula. Euler method and also Runge-Kutta method is explicit method. Okay, what is explicit method? Explicit method when the method compute the dependent variables. Okay, remember the dependent variable, the variables that we want to find. Why? Okay, using known quantities. Okay, using initial value. Runge-Kutta is the fourth order approximation. Euler method is first order. Runge-Kutta is fourth order. And RK method has better accuracy than Euler's method. RK method needs 4 evaluation of, okay, because if RK method needs 4 evaluation of K1, K2, K3 and K4. Okay, we calculate more for RK method. Meanwhile, Euler's method require only 1 evaluation. And RK method has 4 steps that use lower order method for approximation. This step is K1, K2, K3 and K4. While the first 2 steps are predictor. These 2 steps predict what is the solution. Meanwhile, for the rest, step 3 and step 4 is the corrector. Where at this step, they correct the solution. Okay, let's look at example 2. Find the approximate solution of IVP using the same example as example 1. But this time we use Runge-Kutta method. Alright. So for this method, you must draw a table like this. We have I, X, Y, K1, K2, K3 and K4. So same, you must determine X, value of X first. Here is 1, 2, 1.1, 1.2 and 1.3. 0, 1, 2, 3. Okay, the first step is to find K1. K1 equal to HF using this formula. X, I, Y, I. This is the initial value. For K1, K2, K3 and K4, you will use this value of X and Y. Okay, then substitute H equal to 0.1 and F, we want to find F1, Y is 2. So where is our function of F here? So you refer IVP problem, ODE. This one. This is the general solution of IVP is dy over dx equal to fxy. Or sometimes y prime equal to fxy. So to calculate Euler and also Runge-Kutta, you must make sure y prime in this form. If the question is like this, dy over dx plus 2 equal to 2y. You must rearrange first and be like this, dy over dx equal to 2y minus 2. And this is fxy. So our fx is 3x square y. Substitute 1 and 2 here. Equal to 0.1 multiply with 3, 1 square, 2 equal to 0.6. So K1 equal to 0.6. K1 0.6. Okay, next K2. K2 equal to HF xi plus h over 2 yi plus k1 over 2. And then substitute h 0.1 f xi is 1 plus 0.1 over 2 y is 2 plus k1. K1 is the value of k1 here, 0.6 over 2. And then calculate 0.1 f. You get 1.05, 2.3. And then substitute, this is x, y. Then substitute here in our fxy. So 0.1 multiply with 3, 1.05 square, 2.3. Then you will get 0.7607. Okay, next find K3. Panjang. K3 is then substitute here. K2 equal to this value. And then H is 0.1, F, X is 1 plus 0.1 over 2, 2 plus 0.7607 over 2 equal to, don't forget the 0.1, F 1.05, 2.3804. And then substitute this value in fxy, in f, then you will get 0.7873. Okay, next K4. So 0.1 f is 1 plus 0.1. Y1 is 2 plus its value 0.73. Then you will get 1.0118. Okay. Then using these values K1 until K4, you will determine Y1. This Y1. So Y1 equal to, look at the formula. Y1 equal to Y naught plus 1 over 6 K1 plus 2K2 plus 2K3 plus K4. Okay, be careful with 2 here. Sometimes students miss this 2. So Y naught equal to 2 plus 1 over 6, 0.6 plus 2, 2.7846. You have to calculate then again K1, K2, K3 and K4 because we want to determine Y2. After you get Y2 here, then you determine K1, K2, K3 and K4 here. So here we get 4, 0.1414. So this is the solution for this question. 6.6187. Okay, we want to compare the results obtained for Euler and also Archimedes, which the exact solution. If given equation like this is the exact solution. This is the real solution. And the step size is 0.1. And state which method produce better solution. Okay, to compare, first you must calculate the exact solution. Here, this is the column for exact solution. Substitute value of x here. Okay, substitute of value of x here. When you substitute here x equal to 1, you will get 1 minus 1 is 0. Exponent 0 equal to 1. 1 multiplied 2 equal to 2. And then for x2, x is 0, 1, 2, 3. x1. 1.1, you substitute here. 1.1 cube minus 1, then exponent. And we get this answer. Okay. Then this is the approximate solution for Archimedes. Okay, we have 2.7846. Okay, this value refer to this one. Value of y. Okay, for Euler method, take this value. Okay, this value. Okay, percent relative error, you calculate here. Error, exact minus approximate, and then divide by exact. Multiply with 100. So for this one, 2 minus 2, divide by 2, multiply with 100. Okay, so 0%. For second example, 2.7847 minus approximate solution. Then divide with exact solution. This is the exact solution. Okay, we want to calculate the error, percentage of error. We got 0.0036. Okay, this is the error. So this is the approximate solution and this is the real solution. And you will get this is the error for Archimedes and this one the error for Euler method. So you can see that using Archimedes the error is smaller when compared to Euler method. So Archimedes method produce better solution since it has less error. Okay, we calculate numerically. We solve this equation numerically because sometimes ODE equation is very difficult to solve. So you can get this exact solution. That's why now a complicated problem, we use computational numerical method to solve this equation. That's